Well, thank you for your kind. Yeah, it's I think this is a kind of a theoretical nuance. I'm not sure if it's really important or not, but it's kind of fun sometimes to play with theory that has no empirical content to it. So maybe it doesn't matter too much. The first thing is that, yes, we do teach this stuff to students. Maybe we shouldn't, but I think many of you may teach courses in statistics or econometrics. And I'm sure if you teach a class in statistics or econometrics, you have said to a student once in the semester, the sample mean is blue, the least squares estimator is Gauss Markov, or something like that. And so the least squares estimator is very popular. Sample mean is an example of least squares. So it's in the envelope. And we teach this. And what does blue mean? It's not a color. It means that it's the best linear unbiased estimator. And we said, okay, it is a foundational concept for why we do least squares as opposed to something else. And so I want to try to talk about a little bit more about what blue means and replace blue with boo, essentially. In fact, part of understanding is that most people, as I was talking to people earlier, when people say that the Gauss marker blue, forget what the word linear here means. That I think most of us forgotten about it after we learned it, and why it's kind of silly. So the Gauss Markov theorem or the blue theorem say that the sample mean is the best, meaning minimum unbiased linear estimator of the population mean in the IID sampling model. And the Gauss Markov theorem says much the same thing, that least squares is the best unbiased linear estimator of regression coefficients in a homoscedastic linear regression model. Basically, this theorem is 200 years old. And it's called Gauss Markov, but it's really due to Gauss. So let's talk about that. You know, most often in econometrics and statistics, we don't talk about history. And in fact, it's because I don't know much about history, but it's kind of fun. And so this goes back to 1805, back before any of us were born. And Legren published some, I think of one of the most important papers in history of statistics and for econometricians is the method of least squares. And so the question was, how do you fit coefficients when you have more equations than unknowns? And it was really an algebraic issue. You have multiple observations on astronomic units. You have fewer location parameters. How do you do it? And he said, well, it's not that hard. Write down the equations with an error term and take the sum of the squared errors and minimize it. Because it's a quadratic, we have a unique solution. When you take the first order conditions of the set of equations, you get, for k parameters, k equations, k unknowns. I know how to solve that. That's solved by an ordinary method. That is why it's called ordinary least squares. It's because of the first order conditions, k equations and k unknowns. So that's the origin of the word. Now people probably think ordinary means that it's typical or something, but that was the source. And then the idea was spread very quickly because why? It was so easy and such an intellectually, conceptually brilliant idea, you know. Followed up quickly by Mr. Gauss. Now, Mr. Gauss was one of the greatest minds in mathematics ever to walk the face of Earth. His publication was shortly followed. And he effectively was annoyed with this early publication because Gauss says, hey, I already knew this. I did this back when I was 18 years old. The only problem is he didn't tell anyone. So what had he done back when he was 18 years old? He invented maximum likelihood and the normal distribution. So it's pretty phenomenal. But then he published it in 1809. He said, hey, let's think of these errors as being random variables. Huge intellectual innovation, not algebraic, it's probabilistic. And then he says, I want to pick the parameters of the model to maximize the likelihood. He invented maximum likelihood. That's, again, intellectually amazing. He then says, what density of the errors would lead to a convenient solution? And he derived that the answer was the normal equation. He invented the normal equation because it would yield to a convenient answer. So he invented normality to justify least squares, kind of backwards in modern thinking. But he also then derives least squares as solutions. He does all this in one paper. So you have here two papers that are really foundational for econometrics. So he does these kind of things, and I think this huge innovation was moving it to a probabilistic foundation, and all this. And this is also why we call the normal distribution Gaussian. Sometimes we say normal, sometimes we say Gaussian, and because of this connection. A couple years later, Laplace was a great probabilist, introduced the central limit theorem. And this was another way of deriving the normal distribution through averaging. And this then complemented Gauss's assumption of normality, because you could think of the errors in an equation as deriving from things that have multiple causes, averaging to become normal. He also derived an asymptotic efficiency justification for least squares. So what we have then is what we call the Gauss-Markov theorem. So these are some early contributions. This is followed up a 1918-23 paper, again by Gauss. Gauss, in this paper, went back to his old work. So in the 1809 paper, he had introduced least squares, recall, but he hadn't introduced the Gauss-Markov theorem. He did this here. He said, hey, this is not only the maximum likelihood estimator, it's also the best estimator in the following sense, that we now know as the Gauss-Markov theorem. It's the best it's the best unbiased, linear unbiased estimator. Okay, so that's the Gauss theorem. Now, why is it called Gauss-Markov? Because Markov wrote a textbook. That's why I'm writing a textbook. Markov wrote a textbook that was very important in probability theory, and he treated this Gauss theorem. And because of Markov's treatment, it became known as the Gauss-Markov. So my limited understanding of this, it seems unfair really to call it the Gauss-Markov theorem. It's really the Gauss theorem. But anyway, we know of it as the Gauss-Markov theorem. I think one of Markov's key thing is that he really clarified the role of unbiasedness. Gauss had been more vague on that point. Another important contribution in this history is the role of Aitken. Aitken in 1935 generalized Gauss-Markov to the case of general covariance matrices, which is important for some of the things I'm going to be doing here. So this is in the Gauss-Markov framework, but it's technically Aitken's result. So what is a theorem, once again? If it's been a while since you learned it or taught it. Least squares is the minimum variance, unbiased, linear estimator in the homoscedastic linear regression model. So there's a bunch of words here, and they have different points that they come up with. The first one is minimum variance. So that's the efficiency criteria. We want to know in what sense is an estimator the best, the minimum variance. So we shorten that typically in blue to best, but best means minimum variance. If you had a different criterion, it would be a different estimator, right? But that's what it means. So that's really an informal conjunction. Second phrase is unbiased linear estimator, okay? So this is an efficiency criterion. What is this? This is a class of estimators. We have to say, among what estimators are we going to examine? The unbiased estimator is a property of the estimator. Well, it's a good thing. We don't like bias. We're going to restrict attention to unbiased. That's a class. Linear estimators, that's where it's kind of funky, because that is saying it's linear in Y. What's linear in Y means the estimator is an average of Y's. And that's the part that I think oftentimes people forget about in the statement of the theorem, that we're restricting attention to averages. And there's no fundamental reason for that restriction. It's more like I can look underneath the lamppost because there's light there, not because I dropped my keys there. You know, if you know this old story that I lost my keys, I'm looking and say, well, why, you know, where did you lose your keys? I lost them over there. Well, why aren't you looking over there? Because there's no light there. And so here we're restricting to linear estimators, not because we know linearity is good, it's about because we know how to solve the problem. Okay, but this is the class of estimators still. It's still okay. We're gonna have a theorem that says this is the best thing in this class. The final thing that comes up is homoscedastic linear regression. This is the class of data distribution. Say in this class of possible worlds, it says, and you have to make some restriction, because if the possibility of worlds is too vast, we might not be able to say anything. So that's what the theorem says. My goal is, can we remove the word linear from the theorem? Although we have to be careful, there's two uses of linear. There's linear in Y and linear in regression. We're going to maintain linear regression. I want to remove linear from the class of estimators. Can this unbiased linear estimator be an unbiased estimator? And so therefore, is least squares, or the sample mean, the best or minimum variance estimator among all unbiased estimators, which is including nonlinear estimators. So let's go back and talk about the model. So the model is y equals x beta plus e. The expectation is 0. The variance is sigma. This is in vector notation, vector of y's, matrix of x. This is an n by n covariance matrix. Okay, I'm going to be treating x as fixed for convenience, and then a big deal is sigma. Sigma may have restrictions on it depending on what we want to do. You could treat sigma as unconstrained. You could treat it as diagonal, or you can treat it as IID. So we'll talk about all those cases. Unconstrained is a case where of general covariances. Diagonal is when the data are independent, but not necessarily identically distributed. IID is when sigma is equal to identity times sigma squared, that kind of thing. These are all possibilities that we might want to examine. These are all model classes. But that's a model. So it's maintaining that the true conditional mean is linear, because that's what these two things really state here. We're not saying that the truth is nonlinear and fitting a linear approximation. No, it's the truth is linear. You know that's the case. You want to estimate beta. And so how are we going to estimate beta? We do least squares. Well, why? Because it's blue. Oh, we're trying to prove that. Yeah, but so this is one possible estimator. It goes back again to Legendre back in 1805. Then we talk about properties, bias, variance. Bias, we know the estimator is unbiased. Okay, that's a nice thing. Variance, we know that the variance takes this form, and that if we have homoscedasticity, it simplifies that. That's a standard calculation. Then the efficiency question is this the best thing to do, or is there something better? And what do we mean by better is there an alternative unbiased estimator which has smaller variance? You might have so you might object. You say, I don't care about bias. I just want to reduce mean square error. That's fine. That's a different paper. You go write it. But in this talk, we're going to restrict attention to unbiased estimators and try to do the best we can. Once again, what does the Gauss-Markov theorem say? It says, let's restrict attention to linear estimators. Now, what does that mean? It means beta is of the form A times Y for some matrix A, where A is a function of X. And then the theorem says if beta hat is a linear estimator, that is, takes that form, and it's unbiased, then that inequality holds true in the homoscedastic model. And that's one way of phrasing the model. So what is this inequality says that if beta hat is unbiased, its variance depends upon the exact estimator, but it can't be smaller than this. You cannot do better than that. And since we happen to know that this is the variance of the least squares estimator, that tells us that least squares is the best estimator. So there's these different aspects of the theorem, but this inequality is the efficiency statement, effectively, that it's a lower, this is a variance lower bound. You combine that with the fact that you know the variance for least squares, and you know that indeed you've reached the lower bound. So then words, no unbiased linear estimator has a finite sample covariance matrix smaller than least squares. And that tells us that least squares is the minimum variance linear unbiased estimator under homoscedasticity. Some comments. So one of the reasons I started thinking about this, writing this up in this way, is some comments my son made. My son was taking econometrics at a university, and he texted me, I think, and said, "What is this Gauss Markov theorem? My professor makes a big deal about it." And I said, "Don't worry, it's a really silly theorem." And he said, "You're saying, what's this linearity?" I said, "Well, there's two uses of linearity." So I started explaining, and I said, "This is really silly. Why do we teach this to undergraduate economists?" But I didn't tell him he should ignore it, because apparently it was going to be on the exam, right? You know. Anyway, but some comments. It's beautiful theorem in its simplicity. If you look at the way Gauss phrased it, there's only a comment about the first and second moment of the data. Y has a mean of x beta and has a variance of sigma squared. That's all this theorem really says. The only assumptions on the estimator are linearity and unbiasedness. If you look at a modern econometrics paper, the list of assumptions normally takes 10 pages. You know, third order smoothness, derivatives of this, the estimator has to satisfy the following regularity conditions, you know, blah, blah, blah. And then someone has comments after the list of assumptions. All those previous assumptions are standard and easy to justify and intuitive. You know, they may say some nonsense like this. And all they mean is, these are the conditions under which I could prove my results. And so take it or leave it. Anyway, but it's a beautiful theorem, and it's easy to teach. But it also has some unsatisfactory features. And I think the one that I find glaring is that the restriction to linear estimators is an unnatural restriction. I think when I was taught least square Gauss Markov back as an undergraduate, I was told that this was important because linearity is convenient for computation. I mean, doesn't everyone have Stata these days? I mean, you know, all you do is type quantile Q-reg and you estimate a quantile regression. That's easy. It's not a linear estimator. There's no reason to restrict attention to linearity. And it's also kind of funny the way the theorem is written: linear estimators and linear regression, and they have nothing to do with each other. Linear estimators, linear in y is the estimator. Linear regression is the conditional mean is linear in x. They have nothing to do with each other. There's no reason to junk them together. The linear regression is so anyway, that's the thing that I found. I recall my son saying was confusing to him. What was the linearity? Is it linear in x, linear in y? And indeed, it is confusing. Now, why is the sample mean or least squares blue? You know, we haven't. If you teach this regularly, that you might find this elementary, but just remember what's going on. Let's go back and think about the sample mean, because that's really, really simple. So in this case, yi is just an observation, and we're going to talk about the sample mean. Mu is the mean, sigma squared is its variance. Okay, the variance of the whole vector is sigma squared. Sample mean looks like this. So it's a linear estimator. It's an average of the y's with coefficients a, where the a's happen to be 1 upon n. That's what the sample mean is. The question is that a smart choice for a, or could you do better if you put more weight on some observations and some less weight in other observations? And so generally, the class of linear estimators is a linear combination of the y's and vector notation. You can write it that way. And so how do we solve that? Unbiased. The expectation of mu must be the true value, but the expectation of mu is a prime, a vector of 1s times mu. So that is going to equal mu if and only if a prime 1 is equal to the number 1. So that's a restriction on the coefficients. So the question is, what's the smallest variance for all among a satisfying this restriction? And that's the following calculation. What is the variance? The variance is equal to A prime A. So the mathematical problem is minimize A prime A subject to the restriction that A prime 1 is 1. So that's a something we teach, I suppose, in first year optimization theory, beginning optimization theory, minimize a quadratic subject to a constraint. And I think we all know how to do that. The solution can be solved, and you find the solution is that all the coefficients have to be the same, which means they all have to be 1 upon n. So that's the proof that the sample mean is blue. It's a simple algebraic problem. There's one way to prove it. There's other ways. So, but that tells you the best unbiased linear estimator of the sample mean. Then we'll talk about that. Yeah. So that's just under the assumption on the first two moments. But this restriction to linearity is unnatural. We might say, well, what about the sample mean? That's also a reasonable estimator, but that's not a linear estimator in the definition of linearity. Another thing you might think about is I've said I'm restricting attention to unbiased estimators. The question arose before about the distinction between unbiasedness and consistency. They are different. Unbiasedness means the expectation of the estimator is a true value. Is it the case that there are unbiased nonlinear estimators? Because if there weren't, then maybe this is a moot point. Maybe the restriction to unbiased estimators means we are effectively restricting to linear ones. And indeed, the restriction to unbiased estimators is a very, very strong restriction. But the answer is yes, there are nonlinear unbiased estimators. To prove that, I just have to give you one example. And this slide may not be written the best way, but here it is. Sample mean, sorry, that's the sample mean. This is my estimator. Mu hat is the sample mean plus this product. Take the first two observations and take the difference. Take the following two observations and take a difference and multiply the two. This is a quadratic function in the data. So this is linear quadratic function in the data. It's a silly estimator, but it is an estimator because it's a function of the data. But it's also an unbiased estimator because that has expectation of the sample mean, and the observations are independent. So the expectation of the product is the product of the expectations, and these have the same mean. And so the expectation of this difference is just 0. And so I've also computed it this way by looking at the covariances, which are all 0 anyway. You can work out that it's an unbiased estimator. So this is a nonlinear function of the y's, which is an unbiased estimator. What does that simply prove is that we have the class of unbiased estimators and we have the class of linear estimators, and the class of linear estimators is a subclass of the class of unbiased. It's a strict subset. Okay, so when I say I'm going to look at all unbiased estimators, it's clearly bigger than the class of unbiased. May not be very much bigger, but it is bigger. There's some work that has studied nonlinear unbiased estimators in the context of regression, and they've shown that if an estimator is unbiased for this regression model, it must be linear quadratic. It can't be a more complicated function. So the fact that the example I showed you was quadratic was not an accident. If you had more complicated function, it wouldn't be able to be unbiased. So it's a very narrow class. That's okay. It's still a class. And our example is quadratic. Okay. So the question still is, what's the best unbiased estimator allowing for nonlinear? And a possible answer is the Khmer-Rao theorem. So I gather that Mr. Rao was considered one of the great Indian statisticians of all time. Well, he's one of the greatest statisticians of all time. Also happened to be Indian, but he contributed to what is known as the Khmer-Rao theorem. So let's review what the Khmer-Rao theorem says. Actually, what happens in most, I think the traditional taxonomy for teaching Gauss Markov and such in textbook treatments is to say there's Gauss Markov and there's Khmer-Rao, and they give us two different lenses of studying this problem that both give insight. So what does the Khmer-Rao theorem says? It says, this is the general case, not for regression, but the general case. It says, let something have a joint density. So y is a vector. So let y have some density. And it doesn't really have to be a density, it has to be a distribution. But if you have some, it's easier to phrase it in terms of a density. If you have a density which depends upon a finite dimensional parameter, so this is parametric model, and very mild regularity conditions, then for an estimator which is unbiased, not a linear estimator, but an estimator, if you have an estimator which is unbiased, and this again does not restrict to linear regression, it's anything, then the variance cannot be smaller than the inverse of the Fisher information. This is a brilliant result. Yeah, and this is smart. This is so elegant. So an estimator, if it's unbiased, can't have a variance smaller than I, where I is the variance of the score. Just really beautiful theorem. So what is a score? You take the density, evaluate it at the data, take the log and the derivative with respect to the parameter, and then the variance of this object. And there you go. It's also a useful result because if you study the asymptotic distribution of the maximum likelihood estimator, you find that the inverse information is also the asymptotic variance of the maximum likelihood estimator in general context. So what this tells you is that in some asymptotic sense, maximum likelihood is efficient. There's kind of a loose link in the words there between all this, but it's because it's saying that this is a finite sample result and the other is an asymptotic thing, but this finite sample result says that any unbiased estimator cannot do better than that. And it also happens to be that this is the variance in an asymptotic sense of the maximum likelihood estimator. And so that's the reason that within a likelihood type framework, that is a case where you know the true density takes a particular form, it's smart to do maximum likelihood. So this is what we call a variance lower bound. No unbiased estimator can do better. And this is what I said, the asymptotic variance is the same. How do we think about whether this is true or not? Is the proof of the Khmer-Rao theorem is amazingly simple. I have 3 pages on it, but it's pretty simple. The first thing you need to know is that the expectation of the score is 0. And there's a number of ways you can show that. One way is the following. F is a true model. So it's a density. It integrates to 1. Okay, so that's a true equation. And that's a true equation which holds true for any value of theta. Theta is my parameter. For any theta, it's a true model, so density integrates to 1. So I can take the derivative of the left side and the right side with respect to theta. Derivative of the left side is 0. Derivative of the right side, regularity conditions allow you to pull it inside. Derivative of f can be written as the derivative log f integrated with respect to the density. Well, that's an expectation of this object. It's the expectation, so that's equal to 0. So that's the proof that the score is mean 0. And we use that in a step here. Then the next step, you take an estimator. It's supposed to be unbiased because the theorem says if an estimator is unbiased, then the variance can't be smaller. Okay, so we assume the estimator is unbiased. Now the estimator can be written as a function of the data. So theta hat must be a function of y. So I'm going to write it explicitly as a function of y. And I'm going to do that because then I can write its expectation this way. So the expectation of theta hat is the integral of the function of the data with respect to the true density. So this is the true density. Theta hat is the estimator. That is its expectation. And that holds for any something. So it's unbiased. Now, if that holds true for all theta, I can take the derivative with respect to theta. Derivative of theta is 1, I'll assume scalar. Derivative of the right-hand side, it's similar to the proof we had before, which didn't have this theta hat, but now I have theta hat. And I end up with the expectation of theta hat times a score. But I also knew that the score has mean 0. So the expectation of theta hat times something which is mean 0 is the covariance between these two. So this is, I'm just kind of writing this out, but this is expectation of the product is really a covariance because the fact that it's mean 0. So I can write it in terms of theta hat being mean 0. And so this is a covariance. What have I shown is that a covariance is equal to 1. If the covariance is equal to 1, then I can apply the Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality says that the expectation that says that the covariance is smaller than the product of two variances using square roots and stuff. So what I've shown is that 1 is smaller than the product of the variance times the information, which is the same thing as saying the variance is bigger than the inverse of the information. And that's the famous Cramér-Rao theorem. So that's one thing you need to know. A question came up about what if you know the errors are normal? That's the following. So I've kind of brushed through a lot quickly, but in the Gauss Markov theorem said, don't worry about normality, but what's the best estimator in the class of linear estimators? The Cramér-Rao theorem in general says if you have a density, you can't do better than the inverse Fisher information. So let's go to the normal regression model. Normal regression model says we assume y is normally distributed with a scalar covariance. So that is a context where the Cramér-Rao theorem applies. I've done this before in class. That you know that the Cramér-Rao theorem applies. So all you do is you take the density, you take its log, but the normal density is an exponential of a square. And so the log of the density is a square. The derivative of a square is linear, so I get a linear function. And then the Fisher information is the variance of the score. So it's a variance of this linear function, which is that. And then you take the inverse and you get that. And so that shows that the smallest variance in the normal linear regression model is that. And that's the Cramér-Rao theorem as applied to normal regression. If the data is normally distributed, then you cannot do better than that, even among nonlinear estimators. So it does remove the word linearity from the class of linear estimators, but it imposes the restriction that the data must be normally distributed. And so it was not a free lunch. That it came at a big cost. It just says, in the class of normal data, what's the best you can do? So if the data is not normal, this theorem doesn't have any statement. So the way I think people typically say is that, look, least squares is the best thing to do among linear estimators. And it's also the best thing to do if the data is normally distributed, even among nonlinear. Hey, it's a cool thing to do anywhere. And that's the way I always taught it. But then you might say, but what if the data is not normal? So actually, this was a discussion I had. So when I originally wrote this paper, I got in debates with some statisticians saying that my result can't be true, because here's an encounter example. And so suppose the data is not normal. Suppose it's Laplace. What's Laplace double exponential? So suppose that the density of the error term is the exponential of the absolute value. Okay, then you say, what's all the rest? I'm just to scale it, so sigma is the variance. Okay, so now work out the score. Now the score is x times the sine of e. And so the Fisher information is just x prime x. But when you invert it, you get x prime x inverse times sigma squared divided by 2. That's half of the least squares variance. If the errors are Laplace distributed, the Fisher information, the Cramér-Rao lower bound is 1/2 that of the variance of the least squares estimator, much, much smaller. that doesn't prove you can attain it, but indeed, the least absolute deviation estimator asymptotically does. That's saying you can do much better by doing least absolute deviations. So the Khmer-Rao theorem simply says if beta hat is unbiased, then the variance can't be any smaller than this. It's much better than the least squares estimator. It's a smaller lower bound that suggests that you could do better. So it says if the error is Laplace, least squares would not be efficient. So this was the kind of objection that some statisticians were making to me. That's a misunderstanding. And the misunderstanding, it's a complicated nuance, but you have to be thinking about what is the class of estimators. What you've done is that you've dramatically reduced the class of permissible distributions to Laplace and said what's efficiency in that class, not efficiency in the broad class when you don't know. Okay, so what do we know? If the error is normal, which is a narrow class, least squares is efficient. If the error is a Laplace, and these two are not intersecting, they're not, they're very different, then least squares is not efficient. So that would suggest the efficiency bound depends on the unknown distribution. That depends on the distribution. If you think about it that way, I mean, it's technically true, but the misunderstanding stems from the fact that the error distribution is unknown. The right way to think about this in the non-parametric context which is really semi-parametric efficiency context, say, what is the best you can do when you don't know? Because you want to think about the class what is the class for which you want to make a theorem? If you have a theorem that says what's the best you can do on plus distributions, that's fine. It's just that then your theorem is confined to that statement. What you want, but a general semi-parametric efficiency type statement, like the original Gauss Markov, is a statement which does not impose a distributional assumption. So when the error distribution is unknown, what's the best you can do? And if you change the estimator, that means, so one way of thinking about it also is that if you change the estimator, the unbiased property disappears. For example, to gain the efficiency under the Laplace distribution, you would use least absolute deviations. Least absolute deviations relies on a symmetric distribution of the error. If the error was asymmetric, then the LED estimator will no longer be consistent for the same coefficient. You've changed the target. And so you don't obtain unbiasedness in the same class when you change the estimator. Yeah, so, yeah. So, typo. it'd be very biased, yes. What's really the concept of semi-parametric efficiency, which would be more closely related to the traditional Gauss-Markov theorem, is to say, take any model. This is a way to think about semi-parametric efficiency. Is say, we don't know what the truth is, but take a model which includes the truth as a special case, and where theta is some parameter of it. An unbiased estimator, what do we know? Well, the Khmer-Rao theorem says that the variance cannot be smaller than this. Now that holds for all valid models. So this variance must be larger than all such lower bounds. And so the semi-parametric bound is found by finding the worst case. The largest lower bound is kind of a complicated jumble of words, but the mistake in the previous reasoning was doing the imps and the soups in the wrong order. It was trying to find the best case scenario, but the semi-parametric efficiency literature has taught us that you need to find the worst case. You need disciplined by the devil in a way, is the maxi-min thing is you want to do the best possible given that nature throws the worst at you. And so the idea is that if this were the true model, this would be the best you can do. But now suppose that someone says, no, that's not the true model. This other thing is the true model. Then the same calculation, but with the other f, would be the best you can do. And therefore, the best you can do when you don't know nothing is this largest value of all these lower bounds across all those possibilities. It's not the absolute best you can do, because if you think about it the other way, if someone said, well, let's take the inf across all these lower bounds, well, that would be 0, because the best case scenario would be saying that my model class is simply the true f. I know the true distribution. I know the true beta. In that context, my variance of estimation is 0. And that's a rather ridiculous statement. But the point being is that if you make the model class sufficiently narrow, I can do very, very well. And that's not very interesting. The question is, when I approach the data and I don't know what the true distribution is, what's the best I can do? And so you want to define the general model class to be the one that you're interested in. And the context of the so-called Gauss Markov theorem, the context is errors that are mean 0 and have a given variance structure. That's the class that we're interested in. It's not saying under normality, under a Laplace distribution, under a skew distribution. No, it's just the error has mean 0, and here's its covariance structure. That's the class that we want to examine. So how am I going to use this to find the correct lower bound? And there's a shortcut, is that while this inequality holds for all densities, if I find a convenient density which yields a Khmer-Rao bound that yields the answer that yields yields an answer I want in a way, then I can use that to find a convenient bound. And by going through it, I think it'll be more clear what that means. And the answer comes from a tilted density that was introduced to my knowledge by Whitney Newey. So we're going to focus on the case of estimation of the mean. The argument extends to the regression context, but it's easier to understand the context of the mean. And I'm going to focus on the context of an IID sample. So you have an IID sample of data. I want to estimate the mean. I want to estimate mu, the mean of y. It's IID, so all the y's have variance sigma squared. Y has some density f. I don't know it, but it has some density f. And the argument's not restricted to the case of densities. It works for general distributions. And without loss of generality, assume the truth is 0. It makes life easier. I'm going to introduce you a model. It's kind of a fake model or auxiliary model, convenient model. I take the true density and I multiply it by a tilt. The tilt is 1 plus y over sigma squared times mu. Is that really a model? It's a model because it's a valid density in the sense that it integrates to 1. So this is a density of the data. In fact, this is the kind of the way the density works, is that if the original density is the quadratic, 1 minus y squared, and I multiply by this tilt, so I start with a quadratic, and then I tilt it, I get this density. Okay, so I go from the solid line to the dashed line, and the original mean shifts up to there when I tilt it. Okay, and so how do I get that? Is that this is the original density, I multiply it by a tilt, it integrates to 1, and I take the mean, I take the integral of y with respect to the density, and I find that the mean is mu. So mu indeed is the parameter of the mean. The mu is a parameter in this model. It also corresponds to the mean of the density. Okay, so what have I done? I've introduced a model which has one parameter. It's holding, this is, you take it as sigma squared, is that it has one parameter mu, and it is the mean in the model. And it's a true model. So what do you mean it's a true model? You just made that up. You just made that up. What's the definition of a true model? It is a model which includes the truth as one of the special cases. What's the special case when you evaluate it at a specific value of the parameter? That is the definition of a true model. That is, And I obtained the truth by setting mu equal to 0. I set this equal to 0, and the density reduces to F. It is therefore a true model. You said, but that's not a true model because the world doesn't work by that's not the true density. The true density, there's only one true density. People talk about the true family density. No, there's only one truth. There is one true distribution of the data. It's a member of lots of different families. No, there's no such thing as a true family or false family, except for, is the truth a member of the family? If the truth is in the family, then it's a true model. So it's a valid model. So it's a correctly specified model. Correctly specified models like this are subject to the Cramér-Rao lower bound. And it's easy to calculate. So I take the density, I take its logarithm, take the logarithm, and then I take the derivative. And I do that calculation, and I get this. The true density has fallen out of the problem. It's just y. The score is that thing evaluated at the true value of the parameter. The true value of mu is 0. So it reduces just to y over sigma squared. So the score is y over sigma squared. The Fisher information is the variance of the score, n divided by sigma squared. The Cramér-Rao lower bound is the inverse of the Fisher information, that's sigma squared over n. So what have we just proven? We have proven that in this model class, if an estimator of mu is unbiased, its variance cannot be smaller than that. In this model class. But this is a valid model. So that tells us that in general, for any density F, if an estimator is unbiased for the sample mean, it cannot have a variance smaller than that. We have just proven that the variance lower bound for any estimator, linear or nonlinear, is sigma squared over n. But we also know that the sample mean has a variance precisely equal to sigma squared over n. So we know this bound is sharp. So we have just proven that y bar, the sample mean, has this lowest variance among all unbiased estimators, not just unbiased linear estimators. And so we have just proven that, which I call the Boo theorem, best unbiased estimator, if y is IID, if mu hat is unbiased, then its variance is not smaller than sigma squared over n. So when we teach in introductory statistics classes that in this IID sampling model, that the sample mean is the best linear unbiased estimator, we can say that the assumption of linearity is a technical assumption to make the proof easy, but the truth is it's not essential for the theorem. The theorem extends here, and you've all seen the proof now. I mean, there's some technical nuances you want to allow for full generality, but it's basically all there. Yeah. Yeah. Well, we'll talk through some examples because it's true that so question is that what's the role of this IID here? That's this bullet point. So the only kind of key assumption that I was making is that the observations are IID. Technically, I assume that for the way I just showed it to you, that the data has a density and the density is bounded. Those can be avoided. But anyway, but you don't need assumptions like linearity. You don't need assumptions that the errors are normal.
Is this theorem for identical uncorrelated observations?
No. Yes.
Okay, thank you.
So one confusion, so there's a couple confusions that could come place, or like that could be one issue. One confusion is that often comes up is say, well, can't you have an estimator that's more efficient, like under the assumption of class? And the issue here is that effectively what we want here, for the way I phrase the theorem, the best unbiased estimator for all IID observations, it has to be unbiased for any distribution. And so if you say I can do better under this assumption, but then you lose unbiasedness in that, otherwise, then it's not an unbiased estimator. It has to be an unbiased estimator anywhere for any context. Otherwise, what's the point? Like, so sample median is a great estimator of the population median, but it's a lousy estimator of mean unless the data is symmetric. If the data is skewed, you don't estimate the median. If the data is skewed, median does not estimate the mean, it estimates the median. So, you're estimating the wrong thing. So you get reduction in variance by specialized estimators, but only at the cost of bias. And that might be okay. You may not care about bias, but it just, again, within the context of the game plan. Now, there's a couple, we'll come back to this issue about uncorrelatedness in a minute, but there's also, you might think, well, what about the model where Y are independent, but they have different variances? What do we know? Well, we would all, if you've taught this kind of thing, it's kind of a standard exercise to say, well, but think you want to weighted average, weighted squares in the context of least squares meter, and that does better than the sample mean. Does that extend to the context I'm talking about? And the answer is yes. That is, instead of tilting the data by a simple tilt, but using a tilt which depends on these unknown variances, you can show that indeed the variance lower bound is this. And so the statement would be, for data which are independent with a common mean but heterogeneous variances, then if you have an unbiased estimator for the mean, the unbiased estimator's variance cannot be smaller than this lower bound, which is obtained by the weighted averaging estimator. So the weighted averaging estimator, which is an infeasible estimator in general, but it's a conceptual estimator, is the best unbiased estimator. So that's not a big extension, but it's just to be clear. So this is like the generalized least squares. So a little bit more intuition. So this tilted density is perhaps not very intuitive in all what it means. This idea goes back to work by Charles Stein. 1956, he talked about that the lower bound on any unbiased estimator would be obtained by taking the supremum of Khmer-Real bounds over all regular parametric models, or he called them submodels. And he was really focused on this problem of asymptotic variances, but really the same argument applies to finite sample variances. And that's really what the technique I'm introducing comes here, is that you're getting this valid bound by looking at this very cleverly constructed model. And so it's this idea that you're getting a valid bound by looking at the worst. So the correct way to do the Stein semi-parametric efficiency is you look at the worst case among all parametric submodels. I'm not looking at the worst case, I just pick one, and I happen to realize that obtains as a worst case because it equals the variance of a known estimator. So it's a shortcut, an easy shortcut. Another way of thinking about this, trying to get the intuition by looking at pictures, is define bold F as a set of distributions that have a finite variance. And let F sub beta be the class of tilted distributions. That is a subclass of the general class. It includes the truth as a special case. And you can think of it this way, is that this is the class of the distributions I'm interested in. The class I'm interested in is all densities with a finite variance. I want to talk about the best estimation of the mean, the class of all IID data with a finite variance. This is the truth. And then this is this tilted model that passes through it. It is a true model because it includes the true, but it's also a subclass of the general. But Stein's idea was that you can think about what is a Cramér-Borel bound on this subclass, but then spin that line to get everything kind of covered and look for the worst case. And if you find that worst case, that's going to be your variance lower bound. It happens to be, you can calculate it this way. So I think I'm just repeating myself. I'll keep going. Okay, so this is the question that I think you came up. Yeah, so and now I'm going to extend to the regression context. Y is equal to x beta plus e. The errors are mutually uncorrelated, possibly heteroscedastic. What does the Gauss-Markov theorem say? The classic theorem says that if the variances are homoscedastic and beta hat is linear unbiased, then we have a variance lower bound. What is my analog? Extending the theorems we just discussed. If the observations are mutually independent and beta hat is unbiased, then under homoscedasticity, we get this variance lower bound. So what's the big difference between these? Uncorrelated versus independent. And so the traditional Gauss-Markov, at least the way you can prove it, you don't need to have the observations are independent to obtain that lower bound. All you need is uncorrelatedness. Now, what's the difference between uncorrelatedness and independence? Not all that huge in practice, but that's technically the distinction. But for the theorem I just described, it doesn't work under pure uncorrelatedness assumption. The proof technique that I've used only works here with independence because you have to multiply the densities. And so it's not a strict improvement. The theorem is slightly stronger in that. But this is basically the statement here is that if you're in the independent sampling context, the context where the observations are mutually independent, and you restrict attention to unbiased estimators, where they are unbiased, allowing for heteroscedastic variances. That is, I'm not, so it's unbiased in the class of independent observations. Then the variance lower bound, when the truth is homoscedastic, is indeed this bound here. And so that's what this thing is really saying, is that if you have an estimator which is unbiased in the independent sampling regression context, then the variance lower bound under homoscedasticity is indeed this, meaning you can't do, which is what you obtained by least squares, so you can't do better than least squares. So the classical theorem, the Gauss theorem, says that the best estimator among linear estimators is least squares. The one I've introduced says that the best estimator, period, is least squares. And is there a cost? And the answer is yes. The Gauss-Markov theorem allows for uncorrelated observations, but they don't have to necessarily be independent. But my proof, in contrast, relies on independent observations. That's, I think, the big deal here. Not that yeah, that's the thing. Now, a related, I showed you that nonlinear estimators exist for estimation of the sample mean. What about for regression? Is it that different? And the answer is yeah, you can construct nonlinear unbiased estimators in the independent sampling framework. Again, they're kind of kooky, but that's the point. So, this is going to look kind of strange, but this works. So this morning I talked about the leave one out estimators. So the leave one out estimator says, take observation I, throw it away, and re-estimate the model. This estimator is independent of observation I by construction when the data are independent sampling. And then take some observation J, which is different than I, and take yj minus xj times beta without I. So what have I done is I'm creating a predicted value. I'm taking like a residual for observation J using the estimator that doesn't have I. And then I'm going to multiply that by yi and add that to the least squares estimator. That is a nonlinear estimator because I have y and I have y, they're multiplied. So it's a this is a function of y, this is another y, this is a nonlinear function of the data. But you can show that it's an unbiased estimator because of these independent constructs. So like the expectation of the leave one out estimator, unbiased estimator, it's inefficient by throwing out observation I, but that doesn't matter. It's unbiased, and this residual is mean zero, this residual is not a function of I, of the observation I, so it's an independent of I, and so therefore it's independent of this. And so the expectation is the product of this product, and it drops out. And so it's not a very intuitive estimator or anything else. It doesn't really need to be. But the point is that it is possible to construct estimators that are nonlinear functions of the data, of the y's that is, yet it's unbiased. And so therefore when we look at the class of linear estimators and the class of unbiased estimators, the class of unbiased estimators is strictly bigger. And so when we talk about blue versus boo, they aren't the same classes of estimators under independent sampling. And this is important. It's also important for some of the debate that's happened since I wrote the first draft of this. What about, so I mentioned that there's these different error distribution variances and that different classes that we may be interested in. So we can think of the errors of all being homoscedastic. We can think of the error distributions being heteroscedastic but independent, or uncorrelated, or we can think about a general covariance matrix, right? So these different kind of regression model contexts. The Gauss Markov was really applying to the case where the errors are all homoscedastic. But what if they're heteroscedastic, like in the real world, but independent? What then? So we can think about that as if this is in vector notation, think of the variance of the error vector as being a diagonal matrix with the variances on the diagonal. What then would we do? Well, one thing we might do is generalize least squares, assuming that D was known. We would do some sort of a weighted least square, like weighted least squares this way, right? And we know that estimator is unbiased, and we know that this is its variance, and we know from Aitken that this would be the best linear unbiased estimator. But is it the best unbiased estimator in general? Sorry. Yeah, so Aitken's theorem, the blue type theorem, says if beta hat is linear and unbiased, its variance cannot be smaller than this. That proves that generalized least squares is the best linear unbiased estimator. Again, with a caveat that in practice, you really don't know these variances, so it's an infeasible estimator. It's an infeasible lower bound, but at least gives you a target. In practice, it would say that in this model, if this is what you believed, you'd be trying to do generalized least squares or something close to it, because it would be it's like a reference of what the best you can do. What's my analog theorem? It says that if you have observations that are mutually independent and beta is unbiased, then its variance lower bound is the same. So the Aitken theorem does not require independent observations. It only requires, again, the uncorrelatedness. The Aitken theorem says that, yeah. No. The question was, does this extend to feasible least squares? And the answer is no. So to kind of put both of these things in context, a feasible GLS would use an estimated D, and Aitken's theorem clearly does not, partly because the feasible GLS is not a linear estimator. Feasible GLS would be a nonlinear estimator, but I'm allowing for nonlinear estimators. So indeed, I mean, I guess in a way, so it depends on the correct answer to your question. The feasible generalized least squares is indeed a valid nonlinear estimator, but what it fails to be is unbiased. When D is an estimated D, the feasible GLS will not be an unbiased estimator. So it's not in the class of unbiased estimator. It will have bias in practice. So because it's not a quadratic function. Yeah, it is still the case that I think that this theorem has relatively small meaningful applications because of this restriction to the class of truly unbiased estimators, a very, very narrow class.
Generalize least squares extended to time series context, right?
Yeah.
But yours are silent. Because you are considering only independent.
Yes, that is right. Yeah, in that theorem, yeah. Yeah, that result. So I'll talk about the case of general covariance matrices in a moment, but the theorems I'm really referring to here is the independent sampling context, diagonal D. But the context that would apply for time series is some sort of unstructured sigma. So maybe that would be another intermediate case, which I did not explore. So I'm now going to talk about the case of sigma being completely unstructured. But another context of interest might be that sigma is from an autoregressive structure. What then? And I haven't thought about it. Yeah, and again, there'll be that won't be an unbiased estimator, and so, but it's still a model class that's interesting to think about. The context I did think about was the case where sigma is completely unstructured. And just think about, so it's kind of like the clustering context, but not exactly. It's you have y is equal to x beta plus e, and the variance is some general sigma, kind of potentially unstructured. Well, you can think about doing generalized least squares. If you knew sigma, so you're given sigma, you can estimate this, and we know that's unbiased. We know this is the variance, and we also know from Aitken that the variance lower bound is that. So they say unstructured, but it's kind of given to you in that way, or could principally given to you. Now, what is an analogous theorem I can state to this type of result, and it's very simple. Just says that if you have an unbiased estimator, then that's also its variance lower bound. So this is a strict improvement. The Aitken's theorem says if beta hat is linear unbiased, then that's in this. And for this, I do not need any kind of independence assumption or anything. It's a just a statement that you have a joint, y has a joint distribution, and everything has a common mean. X has x beta is the mean, and the variance is some general sigma. So it's a very clean statement of the result, and it's a variance. and it's the same lower variance lower bound. So if you want to think about this as a theoretical statement, you can simply cross off that linearity with no loss in generality, and that is a strict generalization. It may not be interesting because in practice we don't know sigma, but it still is, at least in my view, telling us that this is a target for estimation. Feasible generalized least squares should be a target for estimator, namely this type of estimator is a reasonable thing to do in this sampling context. But there's an interesting corollary, which is that in the context where sigma is completely unstructured, there's no generality of focusing on nonlinear unbiased estimators, because it turns out that if an estimator is unbiased, it also must be linear. So I've pointed out to you that in the context of independent sampling, there are nonlinear unbiased estimators. But in the context of when I've relaxed that to the case of non-independent sampling, general unstructured sigma, then it turns out linearity and unbiasedness are intricately linked. And there's two papers that make this point. And what they make the common point that if an estimator is unbiased for all sigma covariance structures, then beta must be linear in Y. And therefore, if you go back to this statement here, if beta hat is linear unbiased for all sigma, then it turns out linearity is redundant. And therefore, you get this result as a corollary. And so this is an observation that was made more recently, and I think it augments our understanding of the relationship here that in the context where you allow for a general covariance structure, linearity is not really a binding constraint, because it's really the unbiasedness, it requires it. It's just the examples I showed you earlier of nonlinear unbiased estimators really made strong use of the independence of the observations. And so it's relaxed is that if you're going to require an estimator to be unbiased, not with this uncorrelatedness structure, you're going to it didn't require independence, it required uncorrelatedness. It's the uncorrelatedness. If you relax that, then you're going to be in problem. Now, this might see this intuition that says that if an estimator is unbiased, then it must be linear. I remember getting this argument I got this argument with Stephen Portnoy a year ago, and people said, "Oh, it must be true." But turns out that he spent more than a month of his life working trying to prove it, and it turns out to be not an elementary thing to prove. That his proof uses mathematics that are beyond my ability to understand. It's very deep. It's a rather relatively deep mathematical principle, and these guys are a bit. They both use more deep. They both use fairly deep mathematics to prove this. So it's not an, at least I don't think it's an elementary statement. It feels intuitive, but it's not trivial. So this is really what I was saying here. Other people have tried to make comments about. I just thought it mentioned to be fair. There's one short paper by Vinod who thought that this theorem is not very interesting because truly interesting estimators are nonlinear, truly interesting estimators are biased, and so focusing on unbiased estimators is misguided. And I'm pretty in agreement with this. It's just that, as was said earlier, when we teach this, we actually do teach this, and so there you go. And then another statistician, Jim Bassett, has talked about extending these results to median estimation and least absolute errors. And I think it's absolutely brilliantly interesting to think about extending this to define in what sense the median or the least absolute deviation estimator is efficient in much the same concept. That we can think, basically the idea is that in the class of median unbiased estimators, the one with the smallest dispersion is the sample median. Right? It's an analogous statement using the same kind of reasoning that, but you have to change all the words. In the class of median unbiased instead of unbiased, median bias of the estimation of the median, then the one with not the smallest variance but smallest dispersion is the median. So it's kind of cool. And then he's trying to extend that also to least absolute deviations. So just to summarize, it's common when you teach, especially undergraduate econometrics, to say that the sample mean is the best, or least squares estimator are the best linear unbiased estimators. And if you want to save ink, you can cross off that word. And that's it.
Any questions? Yeah. We have a lot of time left. Yeah. Go ahead. Is it possible to figure out zero-sum
the design of the, let's say, unbiased estimator?
Well, I don't know. The classic Stein theorem approach is kind of a minimax argument. I don't know if that's a two-person zero-sum game, but I don't know. Work it out. I certainly didn't.
Yes, we have any. Please raise your hand. Then.
Can it be also true if you apply maximum likelihood estimation?
Sorry?
Technique? Can it be also true?
Oh, well, there's already the Khmer-Rao theorem for that. So I don't. Yeah, this result, I believe, is very much confined to linear regression. I've thought, I mean, so Bassett has this idea of extending it to least absolute deviations. But I've found that the technique really seems confined to that one concept. I mean, and we already have the Khmer-Rao theorem for maximum likelihood. That doesn't feel like it has much else to say there. So.
This is a thing that anyone who has studied econometrics is of interest. So please, students, anyone, please talk to Professor Hansen about any.
Or other things. Yeah. But most often the questions are, how do I estimate the following model? And then my answer is, I don't know. Talk to Jeff Wooldridge or something, but no, I'm teasing.
My question is, Professor Hansen, what made you think about working on this century zone problem?
Yeah, so I got interested in when I was writing up. Actually, this is just something that was in my textbook. I was interested in the problem of semi-parametric efficiencies, but it is really this question of what is the best estimator. And in econometrics, semi-parametric efficiency was written about by Whitney Newey and Gary Chamberlain, I think are some of the seminal names working in that area. And they have demonstrations of how to think about semi-parametric efficiency bounds. I was trying to translate that and put it in a more elementary language that would be accessible to first-year PhD students. And so I was working out this particular argument, which turns out to be really a finite sample argument. And it took me, I'd written this up, I don't know, ages ago, but hadn't really made the full flip to understand that it's correctly a finite sample result until a couple of years ago. And I wrote it up, and I had this as a chapter in my textbook. And then a colleague of mine says, Bruce, I'm teaching this. And it's just like, wow, I mean, where'd this come from? I said, well, it's just, it's just something that falls out. He says, well, you should write it up as a paper. So I did. But the answer to your question, why did I start thinking about it, was to teach semi-parametric efficiency at the level of first year PhD in an as accessible way as possible, because I found that the work of Whitney Newey and others was less accessible.
So it is a research that developed out of teaching.
Yeah, actually, 100%. Yeah.
Okay, so that's quite encouraging for teachers like us, actually, that research can start out of.
I've written a lot of papers which came partly out of trying to teach something.
Okay,
Yeah. Typically, for teaching things at a more advanced level, it's never when you teach something to elementary undergraduates, I'm afraid.
Okay, if there are no other questions, I would thank Professor Hansen again for